Hello, audible. Please make me voice. Yes, please, audible. So this will be also a same question. You can solve this. Hello, yes, please. Today we discuss this and the three phase also we complete. Then from tomorrow we start the alternator chapter, synchronous machines. Okay, please read this. Hmm. So see this question, 20 kVA, 2000 by 220 volt single phase transformer has a primary resistance. When we solve this, there is a transformer, single phase, okay dear. Here, this is your 2000 volt. Here it is 220 volt, no load voltage. This is your 20 kVA transformer. Okay. If we see the equivalent circuit parameter like your primary resistance R1, 2.1 ohm, secondary resistance R2, and leakage reactance X1 is okay. These are the X1, X2, R1, R2. Estimate the regulation at full load under power factor, this condition. So now here three power factor condition are given: unity, 0.8, lagging, 0.8, leading power factor. Okay. So now for this we calculate first turn ratio. K equals to N2 by N1 equals to V2 by V1 or E2 by E1. Okay. It is 220 by 2000. Point 0.11 is the power factor. Now, now we calculate total equivalent resistance as here you write as refers to secondary side. Suppose we calculate secondary side, or either you can take a primary side. Mostly we load side we take. Okay. Total equivalent resistance, that is as referred to secondary side. That is R02. R02 equals to R2 plus C. When we transfer from primary to secondary side, this multiple with K square, resistance. Yesterday we have proven. Yes. Here R02 equals to R2 plus R1 days. R1 days equals to K square of R1. Okay. Okay. R2 plus R1 days equals to R2 plus square R1 means ये हैवी होगी ये फाइल इसमें से ना So here your this transformer is given, okay. This is 2000 volt. Here it is 220 volt. When we apply the load here, cos phi 2. क्या हो रहा है यार? This power factor is, suppose one time is unity, one time is 0.5 for lagging, 0.5 leading, okay. One and two. Power this, yeah. Okay. This is R1 equals to 2.1 ohm, R2 equals to 0.026 ohm. Then X1 equals to 2.5 ohm, X2 equals to 0.03 ohm. Okay. Now, please we calculate the edge refer to secondary side. What is the equivalent circuit of transformer? You know, this is the total resistance, total leakage reactance, and this is your load. And this side at terminal we can make this magnetizing branch here. Okay, got it. Here we apply V1. Okay, this is at node. This is your E2. E2 equals to E1 dash. Here is R01 X01. Correct? Not 1, 2. As referred to secondary side, it is R02 X02. Here it is I1. This is I0. And this is I2 dash. Sorry, I2, because it is secondary side. This is as referred to secondary side, this is I1 dash, okay? These are dash, but this is, now here, this is your terminal voltage V2, suppose, okay, at load. And here is the cos phi 2 load power factor, okay? As referred to, we calculated total resistance, total equivalent resistance. That is R02 equals to R2 plus R1 dash. Total reactance, leakage reactance, X02 equals to X2 plus X1 dash. You know, this is R2 plus K square R1. K square R. Here this is X2 plus K square X1. Now you put the values. This is R2 means 0.026 plus K square means 0.11 all square into 2.1. Similarly here 0.03 plus 2.5 into 0.11 squared. Because turn ratio K equals to 220 by 2000. Okay, that is V2 by V1 or equals to N2 by N1. Correct, it comes 0.11. What does values here? Please. So this is 2.1 into 0.11 square plus 0.026 point ohm, and this will this comes, okay, this much ohm, correct? Therefore, as referred to the secondary side, you know, we know the first we consider, now you write first case, 8 unity power factor. At unity power factor means cos phi 2 equals to 1 unity. It means phi 2 equals to 0 degree. Then sin phi 2 equals to At 0 it is 0. Okay. So if we draw the equivalent circuit vector diagram at 0, suppose this is your voltage V2. You know, at this V2, then this current I2 is in phase with this current, means phi 2 equals to 0 degree here. Now drop in resistance is in phase with current, it means it is here. So from here to here it is I2 R02, and drop in reactance I2 X02. Then E2 is this. E2. This is your V2. Now if you calculate E2 equals to, this is a right angle triangle now. Okay, so this, suppose this is OAB. So from triangle OAB, E equals to, means OB, yeah? OB square equals to OA square plus AB square. Here OA is V2 plus I2 R02 whole square plus I2 X02 whole square. What is your B2? Terminal voltage is 220 volt. So this 220 plus I2 is, now here load current. So your KVA is given, voltage is given, we can calculate at full load, corresponding to full load. Here is estimate the regulation at full load. What is your full load current? Full load current, secondary side, I2. Okay. Now you know your KVA rating by, if it is single phase, then V2 into 1000 also by V2. Then this is 20 into 1000 divided by V2 is 220. What is the current? This 20,000 divided by 220. 993.9. 09. 09 means you can write 91 ampere. Okay. Here, if we put these values, 220 plus 0.91 into R2 is R02, 0.514 whole square plus I2 again it is 9.91 into X02 is 0.06. Then what is your E2? Put 0.06. If they multiply, this comes 5.477 plus this now 90.91 into Just a minute. 90.91 into 0.0514 plus 220. This value comes to 4.67 square plus now this value will come 9.91 into 0.06. This comes 5.477 all square. Put 4.67 all square. Root answer. My dear, it comes to 4.74. You can write this much volts. Therefore, voltage regulation. Percentage voltage regulation E2 minus V2 by E2 you can write, or sometimes V2, okay, into 100. E2 is 224.74 minus 220 divided by, or either sometimes you can write B2 with respect to, okay. It is 224.74. Two 2.107%, okay, at unity. Now, if you write at lagging power factor 8.5 lagging power factor means cos phi 2 equals to 0.5 and phi 2 equals to cos inverse 0.5 means it comes 60 degrees. Yeah? Then sin phi 2 this come 0.866. Okay. Now percentage, if you know everything, then you can directly calculate. Therefore, percentage voltage regulation at lagging power factor. What is the formula? That I2 R02 cos phi 2 plus at lagging power factor I2 X02 sin phi 2 divided by, with respect to E2 or V2 you can calculate, okay?
So for top one, we can't use the same formula.
Yeah.
So for the top one, case one, we cannot use the same formula. We can't use.
This one?
Yes, for that one.
No, because at lagging power factor, this vector diagram is changed. See, at lagging power factor, yesterday I explained, this is your suppose voltage V2. Then current, current is lag. This is phi 2 means 60 degree, suppose. Then, due to this current I2, there is a drop in resistance is in phase with current, okay? So this is I2 R02. And in reactance perpendicular to this, that is I2 X02. Then this vector sum of this all three is this E2. And how we calculate E2? We draw this perpendicular line. Okay, like this. My dear, hello. This distance, this is 90 degree. This angle is also phi 2. Here this angle is also phi 2. Then this is I2 x02. If we take a horizontal, this part, this portion and this portion, if you calculate, this is I2 R02 cos phi 2. And this portion is I2 x02 sin phi 2. And this is V2. Then this is V2. So this total is approximately we may take this, okay? Sorry. Means this length is this, means this length will be this total, the total. We consider this, okay? This is E2. So here E2 equation is, here E2 is V2 plus I2 R02 cos phi 2 plus I2 x02 sin phi 2. Now regulation, this V2 minus V2 equals to E2 minus V2 equals to this only, this part. Yesterday we have solved this thing. Okay, so this is your actually this what it is. This is E2 minus V2 as per your voltage regulation. What is the formula? E2 minus V2 by E2 into 100. Okay, this is E2 minus V2 means this. And at leading power factor, this will be negative. So into 100. Okay, dear. Now you put the values. I2 is 9.91. R2 is R02. This, Power factor is 0.5 here, cos 5 plus. Again, this I2 means 9.91 into X2 is 0.06 into sin phi 2 is 0.866 divide by E2 we have here. E2 means will we assume here in this here please you have to correct this with respect to V2 we calculate, okay? Okay. V2. And V2, what is the value of V2? It is divided by 2 to 0. One five 1.54%. or 5 frequency. Here this is again here 2. 9.91. Easy, but only calculation is large. 0.5 plus 9.91 into 0.06025.866 divided by 220. Right here, this come here. Sorry. As a percentage, you have to multiple with, so we get a 3.218%. Okay. Now third. At 0.5 leading power factor. Same, only negative is come. V2 minus V2 by V2. Here I2 R02 cos phi2 minus same values, 9.91 into 0.05. This value is only or same, okay? Only here it is negative.
सर ये डिनोमिनेटर में हम लोगों ने E2 हटा के V2 क्यों लिया है?
Because you have to calculate V2 is required, sorry E2. So actually in both we have to calculate. With respect to generally, with respect to full load we calculate, but in some cases there is a two type regulation, up and down. Up means we take a V2, down we take a E2. Generally actually with respect to full load terminal voltage. But in some cases, if they ask, like yesterday's question, they ask the terminal voltage also. Then same percentage drop you can calculate, okay? Actually, this is, or either you assume, see this terminal voltage, here this voltage ratio. This is, you assume E2 or V2. 220 is V. Then actually E2 we are calculating, okay? With respect to a terminal voltage, we calculate the since percentage change in terminal voltage with respect to terminal voltage, output terminal voltage. Okay. Otherwise, if you write here E2, then E2 के क्या? Here it is 220 again into 100. In this case, this negative regulation will come. Either you check 9.91 minus 9 into 0.0. It comes negative. This regulation is come negative 1.09%. Regulation come negative minus 0.109. 4% like that. Negative regulation, okay. Now, like in your tomorrow question, they can ask the terminal voltage also in both. Like your transformer terminal, now we consider this T20 is a like no. If suppose this is your at no load voltage, then what is that full load? So this much percentage should be dropped. Okay. This percentage drop will be there. Okay. Then here also, here same is this question. Here it is asked find the equivalent secondary resistance and efficiency. If iron losses are this 80% of the full load, it is like it is related to your efficiency and equivalent circuit. Important question, maybe new type question. Okay. What is the mean by equivalent resistance? Equivalent means total equivalent resistance. Either is it total as referred to primary or secondary side. Or total impedance means including reactance also. Here it is resistance. Then at 20 kVA, suppose there is a one single phase. So here it is 2200 to 200 volt. 25 kVA single phase transformer. Okay. There is a the given equivalent resistance of primary and secondary 1 ohm, and this is given 0.01 ohm. Find the equivalent secondary resistance. So my dear, and here if we put a load, total load in secondary, then this I2 will be there. And here it is cos phi to load power factor. This value of power factor is given 0.8 lagging power factor. I2 we can calculate. So first he is asked equivalent resistance. Total resistance as ref to secondary side. That is R02 means R2 plus K square R1 means R1 dash. R2 plus R1 dash. My dear, this R2 means 0.01 plus K is the turn ratio. So here we calculate a K is N2 by N1 equals to 2 by B1. 200 by 2200. This is the turn ratio. Huh? So my dear, so we can write now this 0.0909 whole square into R1 is 1. This is square into plus 0.0. This total resistance will come. So this is your total equivalent resistance as referred to secondary side. First part. Now he asks full load efficiency. And they give iron losses in transformer 80% of full load copper loss. So my dear, first we calculate. In second they ask a full load efficiency at full load. Okay. First you calculate full load current I2. Your KVA, full load KVA rating into 1000, your full load rate divided by V2. My dear, this is 25 into 1000. It comes 25,000 divided by V2 is 200. 25,000 divided by 200. 125. 125 ampere is your I2. Now, this I2 we calculate. Now we calculate total copper losses at full load or full load copper loss. Or you can write total or full load copper loss total. Now you write full load copper loss. You have to calculate. How we calculate full copper loss? If you know the total resistance as referred to secondary side, then secondary current into total resistance as referred to secondary. Here 125 whole square into what is your resistance? This much watt. This is your copper loss which I could. If iron losses are 80% of full load and iron loss 80% of your full load copper loss. It means 0.8 times of your full load copper loss. Into 0.8. So this copper loss, iron loss will come into 8.25 watt. So this is your iron loss and this is your copper loss. Okay. Now you write kilowatt output of transformer. At full load. Very simple. KVA, full load KVA into, full load KVA into power factor, load power factor. So full load KVA is 25 into power factor is 0.8. 0.8 is your power factor, okay? So this becomes 20 kilowatt. Now we calculate input. Power. That is output plus iron loss plus copper loss. Total losses in turn. Output is 20 kilowatt plus losses are in kilowatt you add. So here you can write 0.285 kilowatt. This you can write 0.228 kilowatt. $20.513 kilowatt. Therefore, efficiency output by input output is 20, input is 25, 20 point. $97.549% is the efficiency. Got it? Hello, nice question. Please. Any doubt here? Hello. Okay. Okay, dear. I put in the this group also.
Now we come to the other portion of this chapter. Three-phase transformer you come. Now, before we discuss the three-phase transformer, this is the connection of three-phase transformer. Basically, before we come to the three-phase transformer, we have to understand the three-phase system or polyphase system, maybe sometimes three-phase, six-phase also. So here, we study the three-phase system. So in three-phase or polyphase system, there is a terms line voltage, phase voltage, line current, phase current, and there is a two type of connection we are use, either a star connection or delta. Okay. So what is the line voltage between two lines, like R, Y, between R, like three lines are there, L1, L2, L3, or R, Y, B. So the voltage between R and B phase, R and Y phase, or the BY phase, RY phase. Okay, like this. But phase voltage is between the phase, one phase, and neutral star point. Okay, or voltage between the phase coil, across the phase coil, particular phase coil, one phase coil, not between the line, across the one phase winding. Then if we take the example of balance star connection, balance means per phase impedance. Like a motor winding or transformer winding are identical. All three phases has a same number of turns, means same impedance. Then RYB, the voltage in balance star connection, line voltage is √3 times of the phase voltage, and line current equals to phase current. But in delta, so there was one question is asked in your transformer. You write the basic equation. So this is the basic equation of star and delta. Please you draw this diagram circuit and you write this equation. There was one question, we discussed also. Now you come to the three-phase transformer. Why it is requirement of three-phase? Because our power generation and distribution in three-phase network system. Therefore, we require a three-phase transformer. Now, if we talk about construction, how we build the three-phase transformer, we can build a three-phase transformer by using three single-phase transformer.
If we have a 3 single phase transformer, we can get a 3-phase connection from that. But we need a 3 single phase identical transformer. So that is called as using a bank of 3-phase transformer. A bank of, not 3-phase, a bank of 3 identical transformers. Second, there is a 3-phase core unit transformer we know. यहाँ पे जो B है ना उसको निकाल दीजिए. A and C is generally the classification. 2 single phase, it is different type connection. Scott connection, for Scott connection we use this 2 single phase transformer. Okay, please know. One is a bank of 3-phase transformer. Second is 3-phase unit transformer. 3-phase unit means there is a 3-phase core. We do the winding, 3-phase winding on that core. So there is a certain advantage and disadvantage. Okay, now this is the connection of 3-phase transformer. How we can connect the 3-phase transformer? Either star-star or delta-delta, or either star-delta or delta-star. Now again, there is a merits and demerits of some connections. Like if we take an example of star-star. So in star-star connection, first in star connection we get a neutral point. Then here voltage across each winding is root, 1 by root 3 times, means less voltage. Okay, but here what is the problem? The problem is for harmonics, third harmonics. Okay, it will be not eliminated. To eliminate third harmonics current, we require an additional winding that is called tertiary winding. But in delta-delta and this star-star connection, we require a balanced load. But in delta-delta, it is suitable for unbalanced load also. And here harmonic, see, the third harmonic is eliminate. It is circulate within the delta, it will not come to the load end. And in star delta and delta star, it means if your primary and secondary side, LV or HV, are in different configuration, then there is a 30-degree either lag and lead, means both primary. If we compare the line voltage of HT side and LV side, please remember, forget about primary secondary side, that is maybe HT, LT. Okay, you use a term HV side and LV side, means if we compare the line voltages of HV and LV side, their vectors are shift. Generally, induced voltage or primary secondary are in same phase. But if connection are different, 2 to 3 phase, there is a 30-degree lag and lead. Okay. Now, if single transformer is there, no problem. But when you connect the 2 transformer in parallel or 3 transformer in parallel, then we can, this is another important essential condition for paralleling for 3 phase. Their connection should be same, means star-star we can parallel with star-star, or either delta-delta we connect with delta-delta. If star-delta, then we can use star-delta. Suppose you connect a star-star with star-delta, then what happens? Their secondary voltages, okay, are out of phase by 30 degrees. Due to phase difference in 2 secondary voltages, there is an internal circulatory current will flow. Now, another very important thing, turn ratio. If we talk about the turn ratio in case of 3-phase transformer, we use a phase voltages, please. Secondary phase by primary phase voltage, because this number of turns are per phase. Okay, per coil. Got it? So this is the important information about the three-phase transformer. Okay. And there was in all the ETO questions that is asked, what is the advantage of three-phase bank over a unit transformer? Now, essential condition for paralleling of transformer. Okay. I will share these notes. Okay. Do not worry. But now I will want to explain. Oh. Just 2 minutes, please. Hello. Yes, please. So suppose we talk about a three-phase transformer. So their working principle are same, like there is similar to single phase. Here insist of one primary, one secondary. In three phase, three primaries, three secondaries. Three phase voltage is induced. They work on mutual induction. Okay. So now we talk about the construction. Okay, how we make first one is a bank of three identical single phase transformers. B is second here B, yeah, we write. A three-phase unit transformer means here bank of means we in this case we have a three single phase transformer. Identical means same turn ratio. We see like this. Have a three single phase transformer, one, then two, okay. So here three primaries, same number of turns. And three secondaries. HVL village. Okay. Now, in this case, you get a 6 windings total in three phase. Okay. Like this 2 here, 2 here, and 2, this 3 windings, okay? Total 6, 3 primaries, 3 secondaries. Then now if you connect in star star to your say this terminal finish and arc, we have short and we give the supply to this terminal here. Same like here. So it is star connection. Okay. So like here, if we see this star means this is your primary side and this is your secondary side. Star. We can connect in delta. Okay. There is a certain if we talk about advantage. So here there is a 3 transformers. Now suppose they are in delta connected. You know, if they are delta connected, we can also connect in this 3 primaries in delta. This and okay, like this. This is primary side is capital letter, na U1 UVW 11. Sorry, W. Here is small U1 V1. U2 V2 W2 secondary side. Okay. So now suppose or R winding. Or this is HV side, this is LV side. Then they represent by R, Y, B or A. Capital A, B, C. This is small a, B, C, like this terminal. Okay. Now this is suppose B phase. Sorry, B phase winding. This is the B phase here. This is B. Okay, this B. Now suppose this is transformer A. This is B. This is C. Correct. So suppose this one transformer is or outage. Outage means become a faulty or this core is damaged. Then we remove this transformer. If your transformer connected delta, so we can operate in open delta. If this winding is removed, we get a like this. This is open delta. This is called open delta. Okay, open delta or VV connection. In open delta, the capacity is reduced. How much? It is 1 by root 3 times of your rated kVA. That is almost it is 57% only. like 100 kV transformer, how much load? So your load capacity is decreased, but we can no blank out situation. We can operate by only disconnect the phase V winding. And see the transportation, lifting, shifting, because 3 units, small size, we can easily, transportation is easy. But initial cost is more because 3 units have you to brought and installation of 3 units you have to install. The initial cost, installation cost is more. But now here replacement cost is easy because only one small unit you have to replace. ऐसा तो नहीं होगा कि तीनों ही all 3 transformers will damage one at a time. Second, spare part are identical. We can use spare of A and B, C like this. But in unit transformer, there is a large single unit. 3-phase core we are used. This is a 3-phase core. Okay, so here. इसमें सभी डायमेंशन सेम रहती हैं, okay? All dimension are same. This core dimension, windows. Suppose this core limb is for R, Y, and B phase like this. So here R phase LV winding. Okay, R phase HV winding. Same like here. LV of Y phase, LV of B phase. Then over this LV you put the HV winding. Okay, so LV, HV of R phase, Y phase, B phase like this. This is, but it is a large unit. Then here transportation is difficult. Then installation, because you are generally actually more space. This is a large size unit, but it is less space required. Here it is more space is required because 3 units you have to install, but there okay, correct. But it is a large single unit, that is a heavy load, lifting, shifting, movement is difficult. It is assembled at site. They can be ready transportation, okay? Because large unit is not a provision to remove and load, okay? There, see, suppose this core is damaged, then entire unit you have to replace. Replacement cost is large. So this is the comparison. Now there is a question on 3-phase transformer. Okay, earlier they are asked like this. It was a very important question. This also, or one is this? It was mostly asked. Here also turn ratio is given. 3-phase transformer, and then he is asked to calculate the secondary side voltage. This is primary side is given if your transformer is connected star delta or delta star. And this is one another important question in 3-phase. So very easy actually. In a container 3-phase delta connected. Here 3-phase delta, when we solve this, it is container ship. On board is we use a delta connection. Again, because delta has an advantage, we can open it in open delta. Second, it is suitable for unbalanced load. Now this is the load here. Secondary side we put a 3-phase load. Now this is given this terminal voltage. Here it is 440 volt force. Here it is 6600 volt. Okay. Seeing from a source of, so this is the transformer primary. Now here suppose this at this 3-phase load. What is the here primary line current? This is a primary means 1 I1, secondary means I2, but it is line here if it is in line. Phase current is here, okay, here. This is phase current. These are the phase current, okay. This is primary phase current, secondary phase current. Okay, primary phase current, secondary phase current, line current. Now this current is given 100 ampere. Now second is this power factor cos phi 2. So load power factor is given 0.8. Now is it determine the current in each coil means this phase current, secondary phase current and kilowatt output of transformer. Very simple. As I told, first because you have to be required for turn ratio, transformer turn ratio. For 3-phase we use a per phase turn ratio, per phase or phase turn ratio. What it is called? Per phase or phase turn ratio. For phase turn ratio, we use a number of turns per phase, means in each winding. Okay, or it is phase secondary phase voltage by primary phase voltage. Phase per phase voltage. Okay. Now it depends what is the connection. Can first we calculate secondary phase voltage. You know, always this mention voltage is always in question. Always in 3-phase, it is line voltage. It is given, but we do the calculation in single phase, and you write the answer. Final answer should be in line in terms of line. But during calculation, we use a phase value. So first we calculate for this to calculate this turn ratio, phase turn ratio, we require phase voltage, secondary phase voltage. Now there is a secondary line voltage is given. What is the secondary line voltage? That is 440. Then secondary phase voltage equals to secondary line voltage. Why? For delta connection, because for delta connection line voltage equals to phase voltage. Okay, so this is V2 phase equals to same. Similarly, because secondary side is also delta, then similarly primary side is also delta. Primary phase voltage equals to primary line voltage for delta connection. So it is also 6. My dear, if it is star, then you have to divide by √3, because in star connection, line voltage, phase voltage equals to line by √3. Okay. the way it is fortunately delta delta, then phase voltage equals to line. Therefore, now you time phase or per phase turn ratio. Very simple. K equals to secondary phase by primary phase. Where secondary phase 440. Same. It comes 0.067. Okay, turn ratio. K. Now, because now please, your primary line current is given. That is I2 line, sorry, I1 line. Primary line current, I1 line, okay? That is 100 ampere. Therefore, primary phase current. Okay, I1 phase. Very simple. I1 line by line current by √3 in delta. In delta, current is √3. Okay. Voltage are same. Line voltage, phase voltage, but current is line current by √3. So just you divide by √3. It comes 57.74 ampere. Okay, 35. So this is your second primary phase current. Now, or hence, now turn ratio. Now, therefore, turn ratio, so if we calculate V2 phase by V1 phase equals to I1 phase by I2 phase current equals to K, turn ratio. Therefore, now we calculate secondary side, secondary phase current. My dear, if you use the per phase turn ratio and you put phase values, we get a phase current. So that is I2 phase. First you calculate phase current. Okay? This equals to I1 phase by K. So this I1 phase is your 57.74 divided by 0.067. It comes 861.72 ampere. So see, this is your phase current. Please remember, and this was asked, so this is the current in each coil. This was asked. Now is asked this part. Second part is asked kilowatt output of transformer. For that, you have to calculate secondary line current. Secondary line current. So for delta, line current equals to √3 times of phase current. Secondary phase current. My dear, it is √3 into 861.72. It comes 1492.1. this is the line current, I2 line. So this kilowatt output of transformer, for three phase it is √3 VL IL secondary side, cos phi. For kilowatt you have to divide by 1000. Okay, please. And this is secondary side, so secondary line current, secondary line voltage, secondary line current, power factor, secondary. My dear, this is given √3 VL is 440 and voltage. Line current we have calculated 1492.54. Power factor 0.8 is given. Divide by 1000. Current into power factor into voltage into √3. Get a 909.97 kilowatt. Okay, dear. Excellent. This also you can try. So here three phase transformer. So here this is your primary side, means N1. This is N2. Okay, and primary voltage is given V1. Then calculate the secondary line voltage. If your transformer, suppose you take a first example, this star delta. Your primary side is star. And secondary side is delta. Please draw the diagram. Here it is V2. He is asking V2 line voltage. Okay. Here you apply the V1 line voltage, that is 6600 volt. Okay. Now, correct. Here N1 is given. Here N2 is given. My dear, per phase turn ratio is N2 by N1. This number of turns are per phase. Okay, this is the phase turn ratio. So it is 104 by 900. Okay. Then now you write here primary phase voltage. You please calculate phase voltage. Primary phase voltage. Your line voltage is given, and star. If your primary is star, in that case you can write primary line voltage divided by √3. My dear, 6600 divided by √3. This comes comes 38105. Spelling is 51 volts. This is the primary phase voltage, because for delta, you write for delta. No, sorry, 4-star connection. 4-star, it is root 3 by 4-star connection. Okay. Now phase voltage, you know, therefore if we write now this turn ratio K equals to N2 by N1 equals to V2 phase by V1 phase. Okay. Therefore, he is asking the V2. We write V2 phase voltage. From V2, it is K times of V1 phase. My dear, this value will come. It comes 0.1155 or 56, you can write. Huh? My dear, this 1156 into phase 1. What is this? 3810.51. Please check. Into 3810.51. 440. It comes 440.33. Okay, this much. Now, therefore, this is the secondary phase voltage. Secondary phase voltage. Now, please you write secondary line voltage, because you write the answer in line voltage and it is asked na line voltage second. Line voltage equals to secondary phase voltage only. Why? For delta connection. Because secondary is, now you observe the connection, and secondary is your delta side. You know here delta side, the voltage across the winding, that is the phase voltage. The voltage across between two lines, that is the line voltage. They are equal, na? Either you measure the voltage here or this. In delta, it is same. So it is V2 line equals to 440. Now you please solve for secondary, if delta star. Okay, so just you use the formula. First you convert the phase voltage. If delta star, then this will be your line voltage equals to phase voltage in primary side. But in secondary side, you apply the phase turn ratio, then you calculate secondary phase voltage. Then you convert it, you multiply with root 3. Okay? Mostly you have to understand now, please. From tomorrow we start the alternator. Okay? In here, DC machine, basic electrical circuit, then in three-phase induction motor, in transformer, lot of things we discuss and solve the all types of questions. Okay, now we take a alternator, then power electronic, numerical. Okay, please. And you
Sir, please share the screenshot of these two numericals.
ये तो वेरी सिंपल है ना, आप लिखते नहीं हैं, इसलिए मैं उसमें पुट नहीं करता हूँ. अगर कुछ ज्यादा रहता है, एक बार शुरू कर दो तो फिर हर दिन फिर वही शुरू कर देते हैं आप लोग. और ऑलरेडी ग्रुप में फाइल में जाइए, सॉल्व करके हुए मैंने हैंड रिटन में डाले हुए. ओके.
Okay, sir. Thank you.